Interesting joke. And I would like to build upon that joke first by giving sort of two sincere apologies. First is that I'm not going to be talking about any of the hot AI topics such as LLM or anything like that. And that's mostly because I'm a physicist. My job is to understand how things work. And the moment you put a black box and say that it just predicts something and the prediction is correct, I cannot work with it. So I have to understand what my model does. So I'm not going to be talking about the fashionable AI, but more towards the conventional sort of AI, which is related with information theory and statistics. Okay. So, and then the second apology is there is a lot of technical stuff here which I do not want to go in. So I have made things a bit easier to the point that some of the things are not really as they should be. But if you want to discuss anything in detail, I would be happy to discuss more about it after the talk. Okay, so let's start with the title. I'm going to talk about exploring the universe with machine learning. So Luca promised you a bit too little. He said we are going to learn the galaxy. No, we are going to do something way bigger. We are going to explore the universe itself. And so today we are living in the golden age of exploration of the universe, in the sense that just like there were explorers back in the past who went out with ships and explored the world, we are doing kind of the same thing today. We are going out exploring the, we're not really going out, but we are exploring our our local neighboring universe and how the larger scale of the universe is, where we are, where we came from, and that is basically what I do. And at the forefront of this effort is the South Pole Telescope, with which I am associated. So South Pole Telescope, so let's start discussing that. So South Pole Telescope is a large 10-meter radio telescope, not exactly radio, it's around 150 millimeters, around 150 gigahertz band, located down in Antarctica. And what this telescope does, and there are some good reasons for going to Antarctica. For example, Antarctica is located at a relative altitude of some 2,700 meters. So compared to Melbourne, which is at an average altitude of 30 meters from the sea level, Antarctica is quite higher. And so that means we have got less, sorry, oh, okay, thank you. We've got a bit less of the atmosphere to see through, which means lesser noise, better observations. Also, Antarctica is so cold that it's way more drier than any desert on the planet. So for example, if you look at the plot below, if you look at this plot below, you see the blue box, which shows the water vapor at South Pole, and it is kind of at least a factor of 3 lower than any other place on planet, such as the second planet is the Atacama Desert in Chile, and that's still like 3 times drier than that desert in Chile. So what this enables us to do is make very low noise observations of the universe. And so what does this telescope observe? So the telescope sees something like this. This is kind of a snapshot of an observation patch of the telescope, and you would see 3 kinds of things over here. So first are the bright sources in green over here, which are point sources created by active galactic nuclei, distant star forming galaxies, and such stuff. Then there are dark spots that you might see over here in yellow, which are galaxy clusters. But fine, what we are basically interested in are these blue patches back there, which are called the which are the primordial anisotropies of the cosmic microwave background. So, what is the cosmic microwave background radiation? So, if you go out and look in the sky, you would see that from all the directions in the sky, there is some radiation coming to us isotropically from every direction in the sky, which is of around 2.7 Kelvin. And this temperature is kind of 2.7 Kelvin everywhere, but there are slight variations in this temperature. So, some spots are a bit hotter, some spots are a bit cooler. And how much hotter or cooler are these points? These are hotter or cooler by around something of the order of 10 microkelvins. So, we are trying to look for a signal of that kind. And so, if you look at this signal on the scale of the entire sky, it literally looks like this. It looks like a Gaussian noise. And so, now you might just ask, how do you interpret this? How do you make anything out of this? This is just a Gaussian noise. And the way and to understand this Gaussian signal, we have to go on and do some physics. So, let us go to the model of the universe that we all know today, and that is the Big Bang model. And according to this model, the universe started sometime back with a Big Bang, and then it started expanding. At some point, it cooled sufficiently so that so that photons started free streaming in this universe, which is seen as this afterglow pattern. And then there were dark ages, then first stars began to form, and then there were galaxies, planets, etc. And then in recent time, the universe has been accelerating because of some dominant force, some dominant component of the universe known as dark energy, which creates a negative pressure and all sort of things. But so what we are looking at today is this very initial phase of the universe, this green patch that we see today. So, that is the first time when the universe cooled to a point that photons were able to start free streaming. And so, this is kind of the cosmic microwave background radiation that we see with the South Pole telescope. But now, how do you understand the universe with it? What do you do of it? I mean, this is a fine story, but what do you do? So, we come to a more formal model of the universe called the lambda CDM model. And what the lambda CDM stands for is lambda stands for the dark energy, and CDM stands for cold dark matter. And so, this model has some very basic components. So, for example, it says that on large scales of the universe, there is only one dominant force that we know about, that is gravity, and gravity is the only dominant force over there. And then there is some component called dark matter, which does not interact with light. Then there is some component called dark energy, which has a negative pressure. And then there are neutrinos and all other physics that we know. Okay, fair enough. Oops. Okay. So, what does this look like? What does this model tell us? So, you put all these equations together. Well, I do not know what happened. I really want to show this simulation. I am not. I was connected through my phone, but
There should be one that's just called.
The link works, but
Wi-Fi. Community hub at the dock.
Which one?
Community hub at the dock.
Community hub.
There's no password. You might have to open a browser. Yeah. Open the network login page thing here. Yep.
Is it done?
Yeah, it looks. Yeah, click on get online over here.
Ah.
Wi-Fi, I have a hotspot. Can you just press save?
Oh, I think we are online.
Yeah, it looks good now. Try it again.
Ah,
Hey.
hey, cool. Okay. So, fair enough. So, we see this background noise from the telescope, which is shown over here in the top corner of this plot. So, that says our universe. And now what we can do is we can put all the physics in our model. And what this model needs is what is the amount of matter, dark energy, and such stuff in the universe. And this model also predicts something of a Gaussian noise like that you see. So, for example, if I change the amount of normal matter, and dark energy over here, it changes the pattern over there. And so, what we want to do is we want to set the amount of matter and other components of the universe such that it looks more or less like the thing that we see. And we don't really do this by eye. The way we do it, is we take this data that we have, and we take the Fourier transform of it and find the power spectrum. And so, what power spectrum shows is what is the correlation of all this structure that we see, all this Gaussian noise that we see on different scales. So, do we see a lot of points at smaller scales? Do we see a lot of points at larger scale? And so, for example, when we change the amount of matter, it changes this power spectrum that you see over here as an isotropy in this plot. So, so fair enough, one can change that. So, one has now a mathematical model about predicting this power spectrum, and one also has observations about it. And so, now the question we want to ask is, given some observations of the CMB, what is the amount of dark matter, dark energy, and such stuff in our universe? So, this is a typical Bayesian parameter estimation problem. We just write out the Bayes theorem, and we say that the probability to find a model given some data is likelihood times the prior over the evidence, and then so what we literally do over here is we evaluate this model thousands and thousands of times, and then see how close is the prediction of our model to the data that we have observed. Okay? So, we need to evaluate this mathematical model multiple times, something of the order of 1,000,000 times. And this is where my problem comes. The thing is, this model has some few hundred equations for L modes in the Boltzmann hierarchy, a few other couple differential equations for modes, for scalar tensor vector perturbations, some dark matter, and other things. So, there are some thousands of couple differential equations that one needs to solve in order to get to this model. The model that we saw previously, I mean, was pre-computed. That is why it was so fast. It's not usually that fast. And so, what happens is that we have to evaluate all these couple differential equations to solve this, and this is a very difficult task. And although we have written some very optimized codes which sort of do this calculation in some tens of seconds, but still when you have to do it something like a million times, this gets too difficult. So, for example, for each model we have to evaluate these equations some 10 to the power 6 times, which means for calculating for about 10 seconds per evaluation, it comes to 3000 CPU hours, and then we have to evaluate some 8 to 10 of these models. There are some 5 to 10 different combinations, and so that goes to something like 150 to 2000 CPU hours, and that's a huge amount of time. Can we do something better? Can we do something about it? And this is where neural networks come in. So, there was this paper by Raisisi and collaborators about physics-informed neural networks, and what these physics-informed neural networks are. I mean, I'm giving a very basic definition of the whole thing. That suppose you have a differential equation, an ordinary differential equation, dy by dx equals fx, and you want to find y. So, you basically integrate this equation and find y. So, now instead of using old finite element integrators, what you can do is you can say that your y, the thing that you want to find, you can substitute that with a neural network, and then differentiating neural networks is a very easy task. You have all this backward propagation and stuff. So, you train now this neural network with a loss function defined as the mean square error of two terms. First term, which says that the differential of the neural network should be close to the function that we want, and then the second term, which says that which is just saying the boundary terms. So, in order to fix the constant that comes with this ordinary differential equations. And so, when one does that, so we did that, and what we found was this. So, we found two things. First of all, for the first plot, we found that our neural networks were able to emulate this solving of ordinary differential equations to a great accuracy. The relative accuracy was around 0.001, but that is not the sort of metric that we want to look. What we want to look is that given this emulator or ODE solver, how good are we able to emulate the solving of our partial differential of our ordinary differential equations compared to any future experiment that is going to detect this cosmic microwave background signal. And so, what you are seeing on the plot on the other side is the best we could get for this signal. So, what I am doing is dividing the error with cosmic variance, and what cosmic variance says is that because you have this universe and it is just one universe that we have, the larger areas of the universe that you see, more is your statistical variance on any observable that you observe. So, if you look at that plot, what you find is that for most of the range that we are interested in, the error is less than 2% of cosmic variance. So, what we have done is by solving it with this neural network approach, not only are we able to solve this ordinary differential equations, we are able to solve it with an accuracy such that no future experiments will ever run into trouble because of its accuracy. And but that is not the only thing advantageous about this approach. When we apply it to Bayesian parameter estimation, what we find is that the two estimates of our so the estimates in blue are with finite difference elements, and the estimates in green are with the neural networks, and what we find that is that they are both identical. Furthermore, what we found was that a model evaluation time was reduced from some 10 seconds per evaluation to 300 microseconds. That's 4 orders of magnitude difference. So we were able to cut down our analysis times by almost 95%, from 3000 CPU hours to some 10 to 15 minutes on my laptop. How insane that is. Now these networks are superbly parallelizable, so we were even able to put those on GPUs, and with just one V100 GPU, we were able to get that time down to 45 seconds. From 3000 CPU hours to 45 seconds. That is how good we got.
And accuracy difference between ODE and this?
Oh, I showed it previously, right? The accuracy difference was nothing that any future experiments will ever run into. Okay, fair enough. And now, before concluding, I'm going to talk about some future work that I'm doing. So I'm doing this work. It's not published yet, but it's something very interesting. So all this thing that I told you right now was dependent upon the power spectrum, and the power spectrum works fine as long as your field is a Gaussian random field, because Gaussian random field is completely defined by its 2-point correlation function, so everything can be said with the power spectrum. But there is something more. There have been theories of universe where we say that there wasn't really a singularity at the beginning of the universe, but there was a rapid phase of expansion of the universe called the inflation. And one of the predictions of this inflation is that there should be some non-Gaussianities present in the cosmic microwave background. Now, the problem with calculating these non-Gaussianities of CMB is that this non-Gaussianity needs to be captured by a 3-point correlation function. The 3-point correlation function is so difficult to calculate because it scales as our maximum scale to the power 5, and our maximum scales go as some 10 to the power 4, which just makes it impossible to calculate. But there is this new approach called information maximizing neural networks. And what this approach does is that you make some simulations of whatever kind of thing that you want to observe. So say, for example, a random Gaussian field with a bit of non-Gaussianity, and you pass it through the summarizing networks. What the summarizing networks do is they create some summary statistics of your whole simulation, and then you construct a covariance matrix. I don't think that C is visible over here, but you create a covariance matrix out of it, which gives you the Fisher information matrix related to this. And then you can define the loss of this network as the determinant of Fisher matrix and the determinant of covariance. The determinant of covariance is only so that we make it we make the modes independent, but that's just for beauty purpose. The important thing is that we take the determinant of the Fisher matrix, and now because the Fisher matrix contains second derivative, contains the derivatives of the Shannon entropy, what we are looking for by doing this is we really want to maximize the amount of information that we are taking out from this network. And so, for example, in this plot down here, we are looking at the evolution of this Fisher information with respect to the number of epochs. And I don't know if this dotted line is visible at around 5. And that dotted line which is visible around 5 is the Cramer-Rao bound, which says that this is the maximum amount of information that one can gather. And we see that within a short while, the network stabilizes at around the Cramer-Rao bound. So what this network is doing is that it's taking all this information, but then it's summarizing it in terms of some summary parameters, which we can use thereafter to extract this entire set of information easily and in a computationally cheaper way compared to the traditional methods of bispectrum or such stuff. With that, I'm off to just the summary slide. So to summarize the whole thing, we made a neural network which reduced the computation time by a factor of some 10 to the power 6, saving a lot of computational costs. And then we are developing some new methods with information theory and statistics to extract optimal amount of information from next age cosmological surveys. And with that, I will take some questions. Thank you.
Questions? Have you looked into like quantum computers for these, like your future work?
The problem is not with the problem is with the amount of data that we are getting. Quantum computers can only do a certain kinds of tasks, and ODE solving is I do not know whether quantum computers are good at those sequential things. But that being said, I'm not an expert at quantum computers. I haven't looked, so I do not know.
Anyone else? Yeah, in the back.
I don't know if you mentioned, but what was the architecture of the neural net?
Oh, so we kind of just used a feed-forward neural network, 5-layer neural network. But what we found was that mostly the architecture didn't matter much as long as it was deep enough.
Sorry, as long as?
As long as it was deep enough.
How
So
big?
more than 5 layers.
5?
Yeah.
Oh, okay.
So it's a very simple network. Yes.
With the information distillation you talked about before last, how do they relate to basic autoencoding?
Sorry, how do they relate to?
How does it relate to just basic autoencoding where you reduce the number of the breadth of each layer and then just track each layer? What network are you using for that one?
Oh, this is also just a feed-forward neural network. There's not some crazy thing going on here. Yes, just some simple feed-forward neural networks. And the thing is, what we found was that architecture didn't matter much. As long as it was deep enough, wide enough, everything worked.
Rather just the constant and the equation, or
Oh,
the input parameters?
the input parameters?
What kind of, what kind, were you feeding images or were you feeding in?
The input data.
So for this,
Input parameters for the neural network.
for the information maximizing neural networks, or for the other one?
The other one?
Hmm?
The other one?
The other one? Okay. So for this kind of neural network, the parameters were literally our functions. So the functions that we wanted to solve. Yes.
The ODE functions?
Yes.
You have a boundary there, so you said you essentially can substitute any equation with a neural network and solve it. That's also, and you said you only need to specify the boundary.
The boundary
What
conditions.
if it's the boundary of the universe that you are?
There are very few things that do not go to 0 at the boundary of the universe. are some ways to tackle the boundaries of the universe. You don't really need the boundaries of the universe. In the universe term, what we need is some initial power spectrum of the initial perturbations that were generated at the end of inflation. So it's kind of a time boundary, not the.
You spoke a whole different language to me. But
So
behind
it's kind of a time boundary.
boundary of the neural network.
So it's a time boundary. This is the boundary of an ODE. So when we are solving the ODE with respect to time, we are saying boundary conditions at some time in the past, and then just letting the whole thing evolve according to the physics that we know.
What does ODE stand for, sir?
Sorry?
What does ODE stand for?
What is the ODE?
Yeah.
What?
What is the ODE sample?
ODE sample.
Stands for.
Oh, sorry, ordinary differential equation.
We've got maybe the last question here.
Yeah, thanks. So my astrophysics knowledge is, let's say, extremely minimal, close to zero.
Same as me.
Given that you've now learned, you know, you've got this very fast, very model that can learn the cosmological background at an extremely high level of accuracy. What questions can you answer with this model now that you couldn't answer before?
Interesting question. So what we are planning to do now is, instead of doing what we have been doing, so what we have been doing is we have a whole model of physics, and we have kind of tried to emulate this model faster with neural networks. What we can also do is just allow the neural nets to discover the ODEs that would describe a data. So what we can do is let some parameters of the differential of the neural network go free, and then just give it some data and make it learn the parameters from this. And so these people have already done this. So these people, if you just search for physics informed neural networks, they have solved some Navier-Stokes equations by doing the same thing. So what they did was they took some data from Navier-Stokes equations, and then they just allowed these parameters to go free. And then the network itself was able to figure out the parameters of this equation. And so what we plan to do now is that, I don't know if you know about this or not, but there is a big debate about some tension going on in cosmology. So the tension is because when we look at the data from very early universe, some 13 billion years ago, we find that the universe should expand at some particular rate, characterized by Hubble constant. So the universe should expand at some particular rate, that's around 68 kilometers per second per megaparsec. But then we look also at supernova data. So supernova are the stars which just explode, and they explode with some particular luminosity. And because we know that they should be of certain brightness, we can put them away, and then, I mean, if they are away, we know that their brightness went down by a certain factor, so we can find the distance to that, and from that we can know how much is the universe expanding and stuff. So the Hubble constant, or the expansion rate of the universe inferred from that, turns out to be around 73 kilometers per second per megaparsec. And now these two measurements are at 5 sigma discrepancy against each other. So there is something definitely going wrong over there, and we do not know what's going wrong. The thing is, not only that, there are also galaxy clusters and other large-scale structure data that we observe from the CMB itself. So like I showed in the first plot, we also see galaxy clusters over there. And these galaxy clusters also put some constraints on cosmology, which agree with the supernova data, so from the data that's in the low redshift universe. So there is something weird going on over there. There's something definitely weird going on. And there have been multiple theories trying to explain this. In fact, I myself wrote a paper saying that because we do not take into account some terms in the equation, this happens and stuff like that. but no one really knows what's going on over there. There is a growing mystery, and we are all growing more and more uncomfortable with that. And what neural nets might do over there is they might say that some component of, say for example, dark matter behaves a bit differently than the usual dark matter that we expect. And if they say that, that will be another huge scientific discovery. So I'm really looking forward to that, but haven't been able to code it up. Sorry? It might be. I mean, there are some competing theories about that.
So there might be a parameter missing somewhere?
Maybe. I mean, we just don't know. We
Means the parsec acceleration?
Sorry?
It's mean the parsec second measure acceleration?
It's how much the universe is expanding in each direction given some distance. So it's like it's like a surface of a balloon. So if you take 2 points further away, they would go faster away. So
Great. Let's hear from Prakrut.
thank you.